Having looked briefly now at inductive reasoning, where we reason on the basis of prior evidence and make imprecise predictions about the future, we're turning now to that other kind of reasoning that is well circumscribed, deductive reasoning. Deductive reasoning, as we've noted, is very much at home in mathematics, where it's the kind of reasoning used to obtain, for example, the proof of a theorem from certain axioms. This gives deductive reasoning the character of certainty, which is potentially a little bit misleading. And as we dive into deductive reasoning now, we'll see that there are traps on the way. There are possibilities for things to go very wrong, as well as the wonderful business of generating certain statements. And this penguin here illustrates just one of the pitfalls that can await us if we're not careful. Now, there's much more research on deductive reasoning than inductive reasoning. In deductive reasoning, there's a certain machine-like quality to the reasoning. That is, we are following a clear set of rules to obtain new statements from old statements. You may remember this in geometry class, for example. But that's not the only reason. To study inductive reasoning, you need to have a lot of experience of the past to generate expectations in order to make predictions. You don't need that with deductive reasoning, so it's much quicker to set up an experiment. Inductive reasoning, because it's about the future, always has this probabilistic element to it, whereas deductive reasoning tends to come with a sense of precision and certainty. But as we said, there's some possible pitfalls here. Now, we're going to look at one particular very famous but rather limited form of deductive reasoning, in which we take a series of propositions or statements about the world, which contain what we'll call implication. That is, they're of this form: if this happens, then that happens. Okay. And we're going to look at a particularly pared down version of this. At the end of the video, we'll open that up a little bit. But we just want to get a flavor of what this deductive reasoning is all about. And so we'll be using a kind of logic first introduced by Aristotle called propositional logic. We'll be encountering statements of if something, then something else. And we'll be restricting ourselves to a very small set here. We won't even be venturing into the complications that arise if we allow statements including the words not and or, which are also logical terms. So we're keeping it very, very simple. At the heart of this is the notion of a proposition. A proposition is a kind of a statement about the world, an assertion. The cat is on the mat. This is a statement which, when it's uttered, can be checked to see is it true or is it false. Now notice that it has to be made somewhere. Someone has to actually say the statement, the cat is on the mat, for that to be true or false. As it is, we don't know which cat is involved or which mat is involved. So there's a sense in which we're reasoning here in the abstract, but to apply it, we would have to be in a concrete situations. Now, if we have a series, we'll restrict ourselves to two propositions, and those propositions are assumed to be either true or false. Then what we're doing in deductive reasoning is deriving new propositions which share the truth quality of our original proposition. So if everything's okay, we've set things up so our propositions are clearly either true or false, then we'll know what the statements we derive from that are. Let's have a look at the simplest one. And this is so simple, it's mind-blowingly stupid and obvious. But we're just going to get used to the form here, which we'll encounter in a couple of variations. This one has the fancy Latin name of modus ponens, and it is indeed the famous first algorithm introduced by Socrates, who said that if you have two propositions like this, if Socrates is a man, then he is mortal, that's one proposition. Socrates is a man, that's a second proposition. If you have these two, then you can, as it were, turn the handle and get another true statement out, which is Socrates is mortal. Verify for yourself that that's quite clear. Now, as we've set it up here, The phrase Socrates is a man can be shown here using the simple variable letter P. And the phrase so-and-so is mortal can be called Q. So if P then Q in this instance is if Socrates is a man, then he is mortal. The second proposition, Socrates is a man, just asserts P. And the proposition which we derive we'll call Q, Socrates is mortal. Notice that we're being a little loose with language here, because in the first proposition, if Socrates is a man, then he is mortal, I've used the words he is mortal. In the conclusion, I've used the words Socrates is mortal. We'll understand those as being the same proposition. So this is so obvious, I think you'd be surprised anyone ever found it worth talking about. But there are three small variations on this that we're going to consider. This one has a similar name, modus tollens, and the first proposition in this series is also if P then Q. But the second proposition, the second of our premises, here is not Q. The last time it was P. So if we have if P then Q as our first proposition, and we have not Q as our second proposition, then we can validly conclude not P. So let's give P and Q values so that we can ensure that this accords with common sense. Now, people like to point out the link between fire and smoke, but in fact, sometimes there's fire without smoke. But there's never fire without oxygen. If you don't have oxygen, you don't have a fire. So we'll use that. And we let P be there's fire, and we let Q be there is oxygen. And then we can put together our first proposition. If there is fire, then there is oxygen. Now we've given P and Q values. So our second proposition, not Q, here is there's no oxygen. And the conclusion that we draw is, therefore, not P, or there's no fire, there's not fire. Again, check for yourself that this makes perfect sense. This is valid deductive reasoning. There's the two of them side by side so you can see the form of them. Both of them are perfectly valid forms of reasoning, identified thousands of years ago. And yet, modus tollens, an argument built with the structure of modus tollens, seems to be more challenging than an argument built with modus ponens. But modus ponens, as I said, has the flavor of being so obvious it hardly bears speaking of. So, given these, let's see if we can do some reasoning. Let's check this argument. Here's two propositions. If Susan is angry, then I will be upset. So P here is Susan is angry, and Q here is I'm upset. The second proposition here is I'm upset. So that's Q. Therefore, Susan is angry. So that's P. So what we have here seems to be if P, then Q, Q, therefore P. Let's think about this a minute. That looks a lot like the two we just met. Except that if we think about it in the real world, let's say the first statement is true. If Susan is angry, I will be upset. I'm very concerned about Susan and her emotional state. As it happens, I'm very upset. But I could be upset because my budgie died. I could be upset because I spilled the cornflakes. There's lots of reasons I could be upset. There's no need that this fact that I'm upset implies that Susan is angry. So this is, although it looks like the other two forms of reasoning, it's what we call a fallacy. A fallacy is that kind of pitfall that we can get into. A logical fallacy leads to an invalid inference. So we've had modus ponens and modus tollens. There are two more, almost identical structures we're going to look at, both of which are fallacies. The first one is the one we just met, and it has a fancy name, affirmation of the consequent. Where do the names come from? Well, the structures we're using have P and Q. The first statement is always if P, then Q. P is the affirmation. P is the antecedent. Antecedent. Q is the consequent, because P comes before Q in that. The second premise here is Q. That means we're affirming the consequent, Q, and deducing wrongly P. So here's an example of this. Let's suppose these two premises are absolutely true. Let's see, does the deduction follow? If I do well on the test, I will get drunk at the weekend. Suppose that's perfectly true. And suppose it's also true that I got drunk at the weekend. It's not necessarily true that I did well on the test, is it? I could get drunk at the weekend anyway, I'm sorry. So this has the same structure as the Susan being angry one we just saw. It is, in other words, a fallacy. Now, I may or may not have done well on the test. What you need to see here is that there's an underlying structure to this argument that is flawed. And here's the second of these fallacies. So we start again with if P then Q, but our second premise is going to be not P. And we're going to deduce from that not Q. We better give those values to make it sensible, and we'll use something similar to the last one. Let's assume if I do well in the test, I'm going to get drunk. And assume I fail the test. It's not plausible to deduce from that I will not get drunk. I could still go and get drunk, right? So this argument here is also flawed. It is a fallacy. And these two logical fallacies look very like the two valid forms of reasoning that we saw. So here's the four of them laid out carefully for you. P is the antecedent, Q is the consequent. The first two forms, the first two presented here are modus ponens and modus tollens, respectively. Modus ponens affirms the antecedent, so the second premise there is P. Modus tollens has as a second premise not Q. But the two logical fallacies, affirming the consequent and denying the antecedent, seem confusingly similar. And all of these show that even if P and Q are both true, we need to be careful in deriving what may seem like an obvious conclusion. The two first ways of reasoning are correct, and the second two are incorrect. So if you want to remind yourself, do a table of these, there's the four of them laid out. Now that shows you that there's a structure to reasoning. That is, under certain circumstances, if we restrict ourselves to just the right form of arguments, we can outline a kind of structure which allows us to recognize valid and invalid arguments irrespective of the content. So these structures underlie reasoning where P and Q may have many different values. And we can learn to recognize valid forms of reasoning from invalid forms of reasoning. Now, given our admittedly very limited set of possible propositions here, these are all the examples that arise. But people have taken this further. This is syllogistic reasoning. The syllogism is this form of argument introduced by Aristotle. But we can make those a little bit more complicated. We're not going to do this in detail. But if we allow our first premise, our major premise, to be more complicated, so we can say all M are P, or some M are P, or no M are P. If we've got more values here for what we're asserting, we also use these all, some, or no for the minor premise, then we get a vast number of possible combinations. So our limited choice gave us four possible forms of reasoning. By opening it up in this way and reaching more complicated examples, this one's unfortunately historical, it's from The Simpsons, all Frenchmen are cheese eaters, all cheese eaters are surrender monkeys, therefore all Frenchmen are surrender monkeys. Now this uses the word all, and if you think about it a little bit, you'll find that it is invalid reasoning. Oh, sorry, it's valid, even though the conclusion is done. So if all Frenchmen are cheese eaters and all cheese eaters are surrender monkeys, then it's true, all Frenchmen are surrender monkeys. Now, this is obviously nonsense, yet if the first two were true, the conclusion would be true. Now, this opens up the space from 4 to 512 ways of combining these. And there's an example given there. I'm not going to step through it. But what you can see is that, first of all, this gets tricky as the propositions get more complicated. And people's ability to tell the difference between valid forms of reasoning and invalid forms of reasoning is, well, it's not great, to be honest with you. Because of the biases that we noted before, people are more likely to make judgments based on what they want to believe or what seems likely to them, rather than peering through an argument to see is it logically valid like this. Remember, reason was held out as the hallmark of the human by Descartes. But when we try to flesh that out, it becomes a bit worrying because maybe we're not so good at reasoning. In a famous experiment in 1979, Marcus and Rips gave people lots of examples of the four that we looked at: modus ponens, modus tollens, and the two logical fallacies. And they were asked to judge each one as either valid or invalid. And I'm afraid, while modus ponens is the case, modus tollens was often judged to be invalid, and the two fallacies were often accepted. So this can be complicated. To finish up with, I'd like to just show you an example of how these structures can be lurking where you might not expect them. And we're going to just have a look at an old poem from 1681 and see that underlying the argument of this poem is one of these logical structures that we've just looked at. This is Andrew Marvell's poem To His Coy Mistress from 1681. And the basic argument is he wants to get her into bed. It's a great poem, and I recommend it to you for fun, but let's just have a look and see the argument that's in there. Had we but world enough and time, this coyness lady were no crime. A few lines later, but at my back I always hear time's winged chariot hurrying near, and yonder all before us lie deserts of vast eternity. And later in the poem, now therefore, while the youthful hue sits on thy skin like morning dew, and while thy willing soul transpires at every pore with instant fires, now let us sport us while we may. So there's a three-part argument here. We've got two premises and we've got a conclusion. The first premise is of the form if P then Q. Had we but world enough and time, this coyness lady were no crime. So if we had all the time in the world, that's P. We have lots of time. Then Q. Then your coyness, your reluctance to go to bed with me is fine. But in the second bit, we get the second proposition. But at my back I always hear time's winged chariot hurrying near. So we don't have lots of time. So this is not P. And his conclusion, now therefore, let us sport us while we may, therefore don't be coy into the sack, is not Q. So he's reasoned if P then Q, not P, therefore not Q. I hope you can go back and see that, he's committed denial of the antecedent. Maybe it'll work for you in the pub someday.